we're going to have, so the inner product of AU with V is going to be the A times inner product of UV. But if you have the scalar here actually, so UAV, okay, so you have a UAV, and if you try to pull out this scalar, then you have to put a conjugate actually here, times UV. So these are some of the basic properties of the inner product that we have here actually. So I'm going to use this. So by this first property, I can pull this sum out. So in other words, for I have this A1 U1 plus A2 U2 plus so on and so forth. So the sum in the first coordinate can be written as the sum actually. So those, I can separate these terms and I can get something like this. I equal to 1 to n and sum of AI, UI and sum I equal to, or maybe used a different index here, j equal to 1 to n and AI, UI. So this is what that you're going to get. And then by this property I can, maybe I should write AJ, UJ. Okay? Okay? And then by this property I can pull these A's out of inner product and I can write them as AI UJs. Then by this second property I can also take this sum out actually, and I can say that I'm going to have I equal to 1 to n, j equal to 1 to n, and you're going to have AI, UI, AJ and UJ. So this is what that you're going to get. Okay? But I can also pull this AJ out actually of the inner product. So I'm going to have AI, AJ and I'm going to have UJ here. UJ here. Okay? So for these calculations, with these calculations, if you get any trouble, as I said that we're going to have regularly 1 or 2 Zoom sessions every week. So if you don't understand anything here, you can ask on those Zoom sessions actually. So what I did, I pulled these two sums out, okay, and pulled these numbers out. So the first number is going to be AI, the second number, when from second component, when you try to pull out the number, you're going to get AJ bar actually, sorry, AJ bar. So it's going to be AJ conjugate by the second property. So what is the next thing? The next thing is that you will have a sum I equal to 1 to n, and j equal to 1 to n, and AI, AJ bar, and since this system is orthonormal, so this UI, UJ will become what you call the Chronicle Delta IJ. And as you remember, we defined Chronicle Delta as that Chronicle Delta IJ is going to be 1 when I is j and is going to be 0 when I is not j. Okay? So what would be this? So if you expand this sum, okay, so this sum will go from what do you call j equal to 1 to n. So you're going to have AI, A1 bar, delta I1, AI, A2 bar, delta I2, and so on and so forth. And up to, or maybe I should write it more explicitly, I equal to 1 to n. I can say that I'm going to have, what do you call, AI, A1 bar, delta I1 plus delta I1, yes, and plus so on and so forth, or maybe AI, A2 bar, delta I2, so on and so forth. And since this index I is an index between 1 to n, so in this sum, at some place, I would also appear actually. So it's going to be AI bar, and delta II plus everything would end at AI, AI, AN bar and delta IN. So this is what that you're going to get. So I expanded this sum actually explicitly. Now, since the I is different from A1, so the delta I1 would be 0. So this term will go away. This term will go away. All other terms will go away except this term. So the delta II is equal to 1, because if the two indices are equal, I and j are equal, then this is 1 actually. So this would be 1. So what is going to remain here is going to be a sum that goes from 1 to n, and you'll have AI bar, and we know the basic properties of the complex numbers, that if you take a complex number and multiply with its conjugate, you're going to get what do you call the magnitude of that conjugate square actually. So this guy would be equal to I equal to 1 to n magnitude of AI squared, and this really completes the proof of the result. Okay? Alright. Now, the next quick observation. So, for any orthonormal system, if you have a linear combination of orthonormal system and you try to compute its magnitude, the magnitude of the linear combination of orthonormal system would be equal to what you call the sum of the magnitudes of the coefficients square actually. Okay, so this is what it says. The next thing that I would like to do, and maybe quick remark or a simple theorem, okay, is that if you have an orthonormal system, so you have an orthonormal system must always be independent actually. It must always be independent. Okay? So what do you mean by that? So if U1, U2, Un is an orthonormal system, then this system is linearly independent. Linearly independent. Okay, so if you have two orthonormal vectors, they must be linearly independent. If you have infinite sequence of orthonormal vectors, they all must be linearly independent. No orthonormal vector can depend on each other. So all orthonormal vectors are linearly independent. This theorem is really a simple corollary to this result actually. So what you need to show when you want to prove that that a given set of vectors is linearly independent. So I have an orthonormal system and I want to prove that this is linearly independent. So the recipe of doing it is that, okay, you take these, take a linear combination of these vectors, say AI, Ui, where I goes from 1 to n, and equate it to the 0 vector. And then try to prove that all of these coefficients are equal. Okay? All of these coefficients are equal. So suppose that you assumed a linear combination of these orthonormal vectors and equated it to 0. So by this theorem, what will happen that if you take, say for example, the magnitude of this AI Ui square, this would be equal to the magnitude of 0 vector, and the magnitude of a 0 vector is equal to the number 0. Okay, so what I did, I just took magnitude square onto the both sides. Then by this Pythagorean theorem, or the result that we proved, this guy, okay, so this identity would equal to I equal to 1 to n, and magnitude of AI square equal to 0. This is what that you're going to get, because this is equal to this. Okay? And so I know that these numbers, magnitude of any number or square of any number, whether it is complex or real, is always non-negative. So all of these magnitudes of ai square are non-negative numbers. And I have some non-negative numbers whose sum is 0. Then what you can say about, what do you call these numbers? These numbers must be 0. All of these. So in other words, a1, this shows that a1, a2, and in other words, this shows that all of these ai squares are 0. So in other words, magnitude of ai squares are 0. And now what are the complex numbers whose magnitude is 0? So the only complex number whose magnitude is 0 is really ai. Okay? So it is 0 complex number. So all of these ai's must be 0 for all I equal to 1 to n actually. Okay? So what is the consequence of this result? Or what is the consequence of this result? That if you have a finite orthonormal system, that in that orthonormal system, all vectors must be linearly independent. They can't be linearly dependent actually. And that allows us to do something interesting. That now imagine you have an orthonormal systems. Imagine you have an n-dimensional vector space. Okay, and in that n-dimensional vector space, you have an orthonormal system that comprises of n linear vectors. Okay, but since these orthonormal system in an n-dimensional vector space are also going to be linearly independent, so this orthonormal system is also going to be what you call the basis of the finite dimensional or n-dimensional vector space actually. Okay. So a simple corollary is this, that if you have a inner product space or a vector space in which is finite dimensional, which is n-dimensional for example, and if you have n orthonormal vectors in it, since they are linearly independent, they will form a basis of what do you call that n-dimensional inner product space actually. Because we know from our first linear algebra course that if you have a finite dimensional vector space, for example, you take R3, in R3, any three linearly independent vectors would form a basis for R3. Because any three linearly independent vectors are must going to span the entire, what do you call, vector space actually. So the next thing that we will like to do is take this discussion to a new level and let's talk about the orthonormal basis actually. So let's talk about the orthonormal basis. Okay. The next is to talk about orthonormal basis actually. So here's a quick definition. So suppose you have a finite dimensional, suppose suppose I have a finite dimensional inner product space, okay, with orthonormal basis actually. I must write it a bit more concretely. So I need to define what is the orthonormal basis. So an orthonormal basis for a finite dimensional vector space, finite dimensional vector space, not vector space, but inner product space. Inner product space is a basis if that basis that is ortho and orthonormal system, that is orthonormal system actually. Okay? So, if you have a basis of a finite dimensional inner product space, that base, and if that basis is also an orthonormal system, then you're going to call such basis as an orthonormal basis actually. Okay? Of the inner product space. So what do you mean by orthonormal basis of a finite dimensional inner product space? Such a basis which is also in orthonormal system, you call such a basis as orthonormal basis of the inner product space. Okay? So here's the thing. So here are some examples. Here are some examples. Okay? That consider I take, say, a vector space that is, say, C4, okay, and consider following vectors. So U1 is, say, let me write that vector as a column, doesn't matter. So 1/2, 1, 1, 1, 1. Let's write U2 as 1/2 U iota -1 negative iota, and take U3 as 1 negative 1 1 negative 1, and let's take U4 as, let's take U4 as a vector that goes like 1/2 multiplied by a vector 1 minus iota minus 1 and iota. So these are the 4 vectors. So what we can prove easily about these 4 vectors, that these 4 vectors form a basis of C4. Okay, basis of C4. So since C4 is what do you call 4-dimensional vector space, then you know from your first linear algebra course that if you take any 4 linearly independent vectors, any 4 linearly independent vectors would form a basis for C4. So you don't have to worry about this, but worry about this spanning actually. They will indeed span C4. So the only thing that we need to verify in order to prove that these 4 vectors are the basis for C4 is just prove that these 4 vectors are linearly independent. Okay? So you may verify. I'm not gonna get into the calculations that how to prove such vectors as linearly independent. We know it already. What you can also show about these vectors, that all the 4 vectors also form an orthonormal system actually. They also form an orthonormal system. And what do you mean by orthonormal system? That if you try to compute the magnitude of each one of these vectors, the norm of each one of these vectors, that norm would be 1. And if you take the inner product of U1 with U2, or U2 with U4, or U3 with U2, and so on and so forth, their inner product would be 0. For example, let's just calculate the norm of, say, one vector. inner product of one vector. Calculate the magnitude of u1. So the magnitude of u1 is going to be 1 square, okay, so it's going to be 1/2. So it is actually 1/2, 1/2, 1/2, and 1/2. This is the vector u1, and its magnitude is square actually. Okay. So it's gonna be what? So it's gonna be 1/2 square plus 1/2 square plus 1/2 square plus 1/2 square. So this would be equal to 1/4 plus 1/4 plus 1/4 plus 1/4, and this is equal to 1. Okay. So similarly, you can calculate what do you call the magnitudes of u2 and u3, but keep in view that what is the inner product on C4? The inner product on C4 is that if you take, for example, two vectors, say x1, x2, x3, x4, as I said, you know, there are things that you have to do before watching this lecture. Okay? So the inner product on C4 is that, okay, you multiply, say, so you take the sum there, say from I equal to 1 to 4, so x1 and y1 bar are xi and yi bar. So this would be what you call the inner product on the C4. So using this inner product, the magnitude is simply going to be, you know, magnitude is going to be simply this actually. Okay. So these are the basic things. Okay. Since we are doing the second course on linear algebra, so I'm going to assume the things from the first course and the chapter 4 that we have read. And similarly, what you can do, for example, is that if you take u1 and take its inner product with the u2, okay, then by the definition that I just mentioned, what you can do is that you have the vectors, so 1 over 2, 1 over 2, 1 over 2, and 1 over 2, and its product with, say, 1 over 2, iota by 2, and minus 1 by 2, and minus iota by 2, and its inner product. And when you take the inner product of this with this, you're going to get 1/4, 1 over 2 multiplied by the conjugate of iota by 4, so it's going to be minus iota by 4, plus 1/2, and 1/2 is going to be minus 1/4, and 1/2 multiplied by the conjugate of minus iota by 4 is going to be plus iota, iota by 2 is going to be iota by 4. So everything would cancel out and you're going to get what you call 0. So it is indeed not a difficult thing to see that these four vectors not only form a basis of C4, but they also form an orthonormal system. So you're going to call this basis as an orthonormal basis for C4 actually. Okay, so this is what is the example of orthonormal basis for C4. What are some of the immediate properties of an orthonormal basis? So I would like to quickly write and prove a theorem about some of the basic properties of orthonormal systems. So as I said, you will appreciate the orthonormal basis or orthonormal systems in given inner product space when you are doing physics, when you are doing, for example, some of applications, because it just makes your calculation hell lot easier. Okay, so if you try to do, for example, your calculations of geometry, okay, in some generic basis, you might need to do a lot of, you might need to suffer a lot actually. But with the orthonormal system, your life becomes much more easier. Okay? Anyway, so here's the next result that I would like to mention, and I would like to quickly say. So let let V be a finite dimensional inner product space with orthonormal basis. Okay, let's assume that I have an orthonormal basis, say call that basis beta, that comprises of n vectors u1, u2, un. So these vectors forms an orthonormal system, and they are basis for the vector space V as per definition. And you take any vector V from this vector space. Then you can say something interesting about this vector V. Okay, the first thing is that the vector, and take any vector V from V, then following are two interesting consequences. The first thing is that every vector V can easily be written as, so if you want to, for example, find if you want to write this V as a linear combination of this, for example, I mean, you might have seen in your linear algebra course that if you want to write a given vector as a linear combination of basis vector, then you do what? So you write your given vector as a linear combination of basis vectors, and then you arrive at a system of equation, and you solve that system of equation, and then you get the coefficients of vectors. In other words, that if I have a vector, say for example, basis, V equal to say AV1 plus BV2 and so on and so forth, say for example, then in order to find these unknown coefficients, in other words, how much V1 I take and how much V2 I take to create a vector V, then you know that you have to solve what you call that system of equation actually. Okay, so because this gives rise to a system of equation, you solve that system of equation in the terms of A's and B's and then find A and B, so that gives you a linear combination.